Hello friends and welcome to this video. We are with the 8th chapter of the subject Advanced Digital Signal Processing and the various applications of signal processing domain. As we have learned in the previous chapter, we are covering here. So right from the signal detection, spectral analysis of sinusoidal signals, for speech signals, for random signals, then the musical sound processing, digital music synthesis, analytic signal generation, compression, transmultiplexes, and oversamplings concerning A to D and D to D operations we have seen, along with how to design the sparse antenna array. From last three videos, we are having the hands-on practice into the Matlab environment for the selected applications here. So in this current video, we are going to have one more Matlab program. That is why the title is Matlab Program 4 Application of Signal Processing. In the fourth topic of the current chapter, where we have addressed spectral analysis of random signals. So I hope random signal is very clear as we have dealt the details in the chapter number 3 and the power spectral estimation of the discrete time random signals into its next chapter. So concerning this particular topic, we will be having a Matlab program developed and the corresponding signal we shall be utilizing for power spectrum estimation using the Welch method. So let us begin with the topic. So here we start with our topic, the topic titled Matlab Program 4 Application of Signal Processing. So as I discussed, out of the several applications for this current video, we have selected the power spectrum estimation here. And here the short and simple task we are going to perform here. So here the aim will be to write a Matlab program and execute the same for performing power spectrum estimation using Welch method. So Welch method we have seen in chapter number 4, where we have dealt the several techniques of power spectral estimation classified into two groups, non-parametric and parametric here. So we follow the same fundamentals for the implementation into the Matlab environment. So let us first of all switch to the Matlab environment. So here we are having the Matlab environment with the latest version here, and to this default scenario we require the editor window for writing the Matlab script. So here we write into the untitled Matlab script. First of all, I will be mentioning a comment line mentioning the purpose of this particular program development in Matlab environment. So I just write here, this is a program for power spectral estimation using Welch method. Welch method we have seen in the 4th chapter after the very simple and popular periodogram technique for power spectral estimation. We have covered the Welch method here. So those fundamentals we shall be utilizing. So first of all, we will like to have clear screen. Also the workspace with any variable, if any, we want to get cleared, and unnecessary Matlab windows also we expect to get closed here. So after this, we require first of all a signal for which the power estimation according to the Welch methodology we can implement here. So here let us modularize this section. This is to generate, this is generating the input signal. So this is a signal we have to generate, and then the power spectrum estimation accordingly we shall do here. So as we have this discrete domain preferred here, so for discrete time representation we require one variable. Let us have it defined as small n, that will start with the value 0 and extend to the value 1000 here with the interval of 1 unit. So these are the integers we have 0 to 1000 here, and taking this particular discrete time parameter here, let us have capital A is the discrete time signal that we are going to generate. So we are having it to be a composite signal. Randomness is also there, one of the component, and next the components are of the trigonometric functions, the repeated ones here. So let us have defined it as 2 multiplied to the sine function. Within the parenthesis we have 0.12 multiplied by the constant pi, further multiplied by the discrete time variable small n here, which is further added to another trigonometric component here, sine function, which is having 0.28 multiplied to the constant pi holding the value 3.14, further multiplied to small n, the discrete time parameter here. So small n, discrete time parameter pi, is a constant here, and now to these two trigonometric functions which are added together, we add certain randomness with the keyword randn, and inside the parenthesis the dimensions we set equal to the small n, the discrete time parameter here. So small n we have defined from 0 to 1000 here. So we end this MATLAB syntax with the help of a semicolon here, and by the next line we will accept certain input information while executing this MATLAB program, and this input is to be accepted from the user right from the command window here. So let us define one variable that is called as nFFT here, as we are going to take the help of the Welch methodology here. We need the fast Fourier transformation implemented here. So for that purpose the order we have to obtain. So let us make the use of MATLAB keyword input within the parenthesis and a pair of single quotes. There we expect to print a message, that is to type in the FFT size here. So we accept the concerned input from the user here, whether the FFT size is 8, whether it is 16, whether it is 34, 64, that way the user will provide us the input, and accordingly our MATLAB program will execute and produce the result. The result is the power spectrum estimation here. Now for the Welch methodology, there it is requirement of selecting a particular window here. So let us assign the window variable as Hamming type here. So for Hamming we provide the input argument 256 here. Next to that we also require one user defined information that is also to be accepted from the command prompt here. So that variable we define to be overlap. So the amount of overlap we need to know from the user, that is expected for processing this particular signal. So let us again make the use of input keyword, and within a pair of parentheses and inside a pair of single quotes we will like to print a message, type in the amount of overlap, type in the amount of overlap at the end, semicolon here. And now here we are going to call the function which is executing the Welch methodology for power spectrum estimation, and as the output arguments there are the two variables, that it is pxxs and here we have small f. So as per the MATLAB syntax, here we have that method p Welch here. Output arguments we have already provided on the left hand side, and the input arguments are the signal which is to be processed. So in the above step we have that particular signal defined as the variable capital A. Then the FFT size information is also to be provided, that we have folded in an FFT variable here. Then here it is another input argument, the number 2. Then the type of the window that we have defined to be of Hamming type, and the amount of overlap here, that is also the user defined, that we are accepting from the command prompt here. So this is the very important line number 14, where we are calling the Welch methodology from the Matlab directory here. So as this particular syntax is giving us Pxx to be the power spectral density after estimating according to the Welch methodology here, now it is time to have a display of the input and the output in terms of the power spectral density here. So here I modularize the rest of the lines as with this comment: display of input signal and its estimated power spectrum. So first of all, we shall have a display of the input signal. So for the display purpose, the simplest Matlab command is plot, and the input argument is the signal that we have generated, that we have named as the variable capital A. So here we will limit the x-axis range, so that will be from 0 to 1000 here. And then to this particular plot we shall have a nomenclature to both of the axes here. So let us have the x-axis labeled. So on the x-axis there it will be the discrete time variable small n, index variable, and to the y-axis here we are having the display of amplitude here. Next to that there shall be a short title to this plot. So the title is input signal. So this is what the nomenclature to the particular plot of the input signal generated here. Then after the Welch methodology is executed for power spectral estimation in a separate Matlab window, that is why I am making the use of figure as a keyword here, then the use of plot command, where the input argument is f by 2 comma 10 multiplied by, the multiplication is by the asterisk in the Matlab environment, log to the base 10 of, we have capital P suffix xx here. So Pxx is the power spectral density, and we are having the logarithm of it multiplied by 10. The base of the logarithm is 10 here. So this is having the information plotted in terms of decibels here. Now for labeling to axis here, so we have the x label. So to the x-axis we are providing the nomenclature as slash omega to print the omega sign here, the Greek symbol, and this is in the numerator, whereas in the denominator we have pi. So slash pi is the syntax. At the end we are having the semicolon. So after labeling the x-axis, let us have labeling of the y-axis here. So to the y-axis we write power spectrum, and as this power spectrum is in decibels, comma, we provide dB as the symbol of decibels here. And next to that, after these labeling two axes here, we provide the title to the output plot here. So inside the parenthesis we have a pair of square brackets where we write overlap is equal to the overlap is followed by num to star here. So the keyword is num to str. Within the bracket we have the variable named overlap, that is accepting the input from command window here, and after that we are having the samples here. So this will be the last line of this MATLAB program here. So let us first of all save this MATLAB program. So I just save this with the name program, as we are here in the 8th chapter underscore 8, and this is the 17th topic. So underscore 17 dot m will be the file extension. We save it. So this is the MATLAB folder on the desktop, and here you see the file that has been generated here, and see the label that it was untitled in the editor window. Now it has the name program underscore 8 underscore 17 dot m here. Now it's time to run this particular program. So as I run this particular program on the command window that it was initially with clear screen here, there it is a message printed, type in the FFT size. So let us for example have the information to be 8, and after hitting enter it is asking another information, type in the amount of overlap. So initially let us have it 64. As I hit enter here, you see there are two MATLAB figures have got popped up here. So they have been labeled figure 1 and figure 2. I keep them side by side. So in the first figure, figure 1, you see input signal here. On the horizontal axis, you see the markings from 0, 100, 200, 300, this way up to 1000 we have, and the discrete type variable small n is also displayed here, whereas the vertical axis is from -6 to +6. At the middle there it is the 0 amplitude level, and this is the amplitude information as printed here. So this is the input signal which is given to the Welch methodology. So we have the x and y informations, so in this particular plot, and now in the figure 2 we have the overlap is equal to 64 samples for this power spectrum, as you see on the vertical axis in terms of decibel plotted against omega, the angular frequency, divided by the variable pi here. So I just close these windows, run this program again. So this time let the FFT size that it is asking, type in the FFT size, keep it the same 8, and now type in the amount of overlap. So this time let us increase the overlap, let it be 128 here. So as I hit enter again, the two MATLAB windows have got generated that I have separated. It is the same input signal. So the input signal is not user defined, we have a fixed logic as we have developed. Now for the overlap of 128 samples here, you see the changes onto the vertical axis readings for the power spectrum in terms of decibels here. Now as I close this particular windows and run this again, so it is asking the information for FFT size. This time I increase it from 8 to 16. The overlap, let us say this is initially 64. So again we have the two MATLAB figures. Now you see for the given details from the user, from the command window, you see in the output window the power spectrum has a different nature as compared to the earlier case here. So this is for the overlap of the 64 samples here. So this is the corresponding plot. As I run it again for the 16 to be the FFT size, if I increase the overlap amount to 256 and hit enter, so here we see the nature of the power spectral density seems to be the same, but the decibel levels of the power spectrum have got changed according to the changes into the inputs from the command window here. So this was our topic, MATLAB program 4, application of signal processing. By the next lecture we shall have another MATLAB program. So there it will be some another application of signal processing that we have already learned into the current chapter and the previous also here. So the hands-on practice into the MATLAB environment for the signal processing you shall see. Thank you.